Right. All right, perfect. Well, this is a crowd. Well, thank you a lot for everyone for coming today. And this is, I believe, the fourth panel in the series that our Foundation Probability seminar has been doing this semester. And today, our topic is on Cournot's principle and the best system interpretation of probability. I'm sorry, I have some. All right, and then we have a great line of speakers. We have here that is Isaac Wilhelm, Ryan Martin, Alan Hayek, and Snow, our own Snow, joining us today. And so how do we, Snow, how about this? We're just gonna do things as we did before, and I think just in the order that the four of you are listed, each of you would have about 10 minutes to talk about some things, your thoughts about the subject, and then we'll be opening the discussion and have an open floor discussion. And we'll be picking questions. You can either raise your hand or put your question in the chat, and then we'll just be going in the order that we receive them. All right, so how about, let's start with Isaac. Isaac, do you want to share if you have any slides, do you want to share them?
I don't have any slides, no.
Okay, in which case, please take away. I will be giving you sort of a reminder when we're kind of close to the time mark.
Okay, yeah. Thanks. Yeah, so thanks very much for inviting me, and thank you very much for organizing this. I thought this was a really interesting topic to discuss. So on the question of so my main view of Cournot's principle and the best system interpretation of probability is I don't think they're in conflict, and I think they're addressed towards two different things. So I think Cournot's principle is a principle of rationality, and I think the best system interpretation of probability is a principle of metaphysics. I think that there is overlap, and I think that part of the justification for sort of each proposal, one way to justify each proposal is to draw on the other, but I don't really think of them as competing. I think of them as complementary. That reflects a sort of more general view about the relationship between typicality, which obviously talked about a lot, and probability. I don't think of typicality and probability as sort of competing metaphysical posits either, or competing posits that are support to kind of offer types of explanation that where we have to choose. I think of them as just different chunks of the real world, and I think of them as and I think of the explanations that they support as just related but distinct types of explanation. So to say a little bit more about oh, thank you. Yeah. So let me just say a little bit more about that. That's what I prepared. So I think of, sorry, I should say I'm going to keep referring to typicality throughout this little brief talk, and that's because I sort of understand Cournot's principle through that lens. I don't actually think that's a necessary way to do it. It's just my preferred way to do it. And I think that using typicality helps us see that there is less conflict going on than we otherwise might have assumed. I think when you use like probability to understand Cournot's principle, you start to see conflicts where there aren't any. Okay, so so Cournot's principle is, as I understand it, a principle about how your beliefs should work. So my preferred way, and I presented it in this seminar before, of understanding Cournot's principle goes something like this. I call it the typical principle. If something is typical among the possible worlds, and I say I'm focused on the physically possible worlds for reasons I can get into if people want to know. If something is typical among the physically possible worlds compatible with your evidence, then you should believe that's something. And then the principle is just silent on other things. So unlike some formulations of Cournot's principle, this way of thinking about things doesn't say that if something fails to be typical, you should suspend or anything like that. It just says that if something is typical, then there's a rationality requirement to believe it. Now, there's a question as to why that would be a kind of plausible principle of rationality. Why is that something that should guide our beliefs? And there are several answers that one can give to a question like that. The answer that I prefer is very best system-ish. So, and it's motivated by certain sort of standard presentations of the best system account of probability. So I think of statements about what's typical as serving to concisely and informatively summarize states of the world. So an example that I talk about in my paper typical is if you're told that typically bobcats have short tails, and there are, for the sake of the example, 10 bobcats, and the contextually relevant threshold for what it is to be typical, this is a whole other issue, difference between typicality and high probability, but there's a contextually relevant threshold for adjudicating typicality claims. If that threshold is such that at least 90% of the things in question in this context have to have a short tail in order to qualify as typically having a short tail, then a quick calculation shows that there are 11 different ways, if I remember, if I got this right, a very small number of ways, around a dozen ways to for the property of being short-tailed to be distributed across the 10 bobcats such that it's typical that bobcats have short tails. And then of course there's, whatever it is, 2 to the 10 minus that, 2 to the 10 minus 11 ways for that to not be typical. And so by hearing this typicality fact, so that what this typicality fact does for you is very concisely, because it's just a sentence, typically bobcats have short tails, and very informatively, because it rules out 2 to the 10 minus, I think, 11 possibilities, summarize a sort of kind of physical situation that is in fact obtained, the kind being that bobcats typically have short tails. So obviously that should ring a lot of bells about, the best system interpretation of, ring a lot of reminders that, that's a very best system sort of approach to typicality that's similar to best system interpretations of probability. So you might be wondering, what's the difference between these two things? And I think the difference, so what's the difference between sort of this kind of concise, informative approach to understanding a typicality fact and a concise, informative, summarizing approach to understanding a probabilistic fact? I think the difference is that the typicality fact is about how big stuff is, and the probability fact is about how frequently stuff happens. So, and those are just different. How big a set is, the area of the surface of a table is just a different sort of fact from a fact about a random distribution or a relative frequency, even though obviously they can be modeled by the same sorts of, mathematical functions. In this paper that I presented to this group before, after presenting to this group and getting a lot of helpful comments, I added a rant about what's going on with that similarity of mathematical representation, where I described what Kolmogorov showed, or Kolmogorov's achievement in a way that I think highlights this difference between being about size and being about frequencies and random distributions. The way that I put it was that Kolmogorov's great insight was to realize that our best mathematical theory of size could serve as a stand-in for frequency facts. Our best mathematical theory of size at the time was, of course, measure theory. It was developed, of course, for integration, for the purposes of performing certain sorts of integrals, which, of course, was that is sort of a goal that's much more kind of about the sizes of certain sorts of sets than it is about the frequencies with which certain kind of events obtain and are distributed. The only complaint that one could make was that Kolmogorov's insight and success was so good that it led a bunch of people, I pick on philosophers, but I think statisticians as well, to make the conceptual mistake of thinking that a size fact is identical to a fact about frequency, because the great mathematical theory of size could be used to represent and kind of serve as a stand-in for certain theories of frequencies, and of course by frequency being more colloquial, what I mean is probabilities. Kolmogorov sort of people were led into making this kind of mistake of identifying two different things, how big something is and how frequently it happens. That's a common type of mistake. It shows up all over philosophy. One piece of math is used in two different ways, and so people identify the things that it's being used for when those things are in fact distinct. But there is still a very important distinction there, and I think that distinction, if keeping that is, so in my view, keeping that distinction in mind helps us see how, you know, typicality and probability are about very different chunks of the world. So it addresses that kind of more local concern, and then it helps address this bigger concern, this bigger issue that we're all going to talk about today. I guess I should wrap up. That we're all going to talk about today, because about Cournot's principle and the best system criterion, because the best system criterion is about this, articulates this probabilistic constraint, whereas excuse me, Cournot's principle articulates a probabilistic constraint. And once we see that those constraints are articulated, you know, on the basis of different chunks of reality, the probability chunk and the typicality chunk, we see that there isn't any competition here, because they're just two different, they're just two different types of principles about two different types of two different types of facts in the world. Okay, I'll just stop there, but thank you.
Thank you, Isaac. Just a reminder, I guess, if you have any questions or want to start a chat on the side about things that any of our panelists have spoken or will be speaking, feel free to do so in the chat box on the side. And you know, we'll reserve the questions and discussion towards the end. So next up, we have Ryan Martin from NC State. Ryan, you're the statistician in the house today. Please take it away.
Okay, so I made some slides, so I need some.
Oh, you need let me.
Yeah, just so you don't have to stare at me the whole time.
Do I just make Ryan co-host? That would allow him to share.
Yeah, or you can just use the share screen. Actually, just make him co-host might be the easiest way.
Let me see. All right, Ryan, try again.
Yeah, it looks like I can do now. Okay, that looks okay.
Perfect.
Okay. Okay. Well, great. So, yeah, thanks for invitation. So, yeah, I'm the lone statistician on panel. So, do my best to keep up. So these are the questions that Glenn had sent in the email. So I guess a number of these things, these are focused mainly on kind of comparisons between this Cournot's principle and some of Lewis's best system and maybe some related things. I was glad that my assessment of this was knowing very little about either of these things. I thought my assessment was that these things are not in conflict, and so some of these questions are kind of leading towards comparisons or maybe trying to compare and contrast these different principles. And I thought I was glad to see that, glad to hear that Isaac mentioned already that he didn't think these are in conflict, because that was also my feeling, is that I think that these are. I guess in some sense I would say that sort of Cournot's principle is sort of a kind of a base level of something for probability to be meaningful, that this should satisfy some kind of connection to the real world in this kind of way. So anyway, so I consider myself probably less than even an amateur philosopher. So I didn't want to attempt to try to talk about these things in any sort of real generality. So I took the liberty of essentially abandoning what Glenn had proposed that we talk about, and focus the attention, rein things in and focus on some stuff that I think that I guess I have some experience with. So I want to talk about these Cournot's principle and some of Lewis's ideas in the context of specifically of statistical inference. So then I'll have some things here. So there's some symbols here, but this is meant to be fairly non-technical. So just as a very basic sort of setup for a statistical inference problem, you have data, of course, and then there's some distribution here. So I'll give some more about the interpretation of this probability P here shortly. But then there's something that I'm interested in that's related to this P. So let's call it some function, I'll say, of P, this theta. And so the setup that I'm interested in is one where we have no prior information, so more in this sort of classical sense, I guess, in a Fisherian sense. And so what I take as the goal here of this probabilistic type of inference is that I'd like to be able to assign something like probabilities to hypotheses about this unknown. So what this ultimately requires is that I can construct some kind of a data-dependent, I'll say, quote here, probability on that parameter space. And so this thing doesn't actually have to be an ordinary probability, could be something else. So in my work, I actually am often working with lower and upper probabilities, much like Glenn's belief in plausibility functions. So the natural idea here is that, well, okay, if I can assign these probabilities on that space, then I want to use these probabilities to make inference. And so I guess maybe the obvious way that you could do this is say, well, if there's a hypothesis that gets assigned small probability, then I want to infer the complement. So it's of course you can imagine maybe it's not so difficult to write down these probabilities, but in order for these to be useful, they need to be reliable in some sense or meaningful. And so that'll be kind of where this Cournot and Lewis's ideas show up. But I guess it makes sense. I wanted to sort of point out is that this, I think, ultimately was what Fisher was trying to do with his fiducial argument, was come up with ways that you can construct these probabilities that give that lead to some kind of meaningful inference. And so I think this is still an important and I think mostly unresolved problem. So what I think is interesting about this one is there's actually two probabilities at play. When I was looking at some of the materials about Cournot's principle and about Lewis's best system. So these are usually thinking about we're attempting to describe the real world somehow. And so usually there was just sort of this one notion of probabilities about what's going to be observed. And so here there's actually two things happening. There's one probability, which I'll here refer to chance. And I think so P, and this can really take any kind of interpretation that I think that you like. So this could be frequency, or could be objective, could really any of these kind of things. But it's this other object that's those probabilities that I'm going to be defining as the data analyst. And so those things are necessarily subjective, like a sort of a credence. And those things are somehow they depend on data, but these are things that I specified, so they're internal to me. But in order to achieve that goal mentioned in the previous slide, there needs to be somehow a link between these two things. What makes this, my credence relevant to the real world? So there's I think a basic idea here, which is just in words, you can say is that the chance that I end up assigning some credence, or let me say it this way, the chance that my credence leads to some erroneous inference, I ought to have some control over that, right? To make sure that doesn't happen. The chance of that is relatively small. So I think that this idea, I don't claim any sort of that this is really a new idea. I know that I think Phil is probably here. I think he has something that I think is related to this. It's called the production principle. So that actually, I think in words at least, sounds very similar to what I have written here. But I wanted to talk here about kind of what do I think that this notion of validity has to do with Cournot and Lewis. So like I said, this probability that I create, this is necessarily subjective. And so what is it, in what sense, and how is this possibly relevant to the real world? So I think at the minimum, this is a meaningless statement, but to say that it shouldn't be externally meaningless. But I think what I think that means is that in this case where I assign some small probability to this hypothesis, that somehow that should carry some weight, that should make maybe others doubt the truthfulness of that hypothesis. So I think that this boils down to something kind of like Cournot's principle, but it's on this sort of very subjective domain where there's not anything like a real life. So what I want to be able to say is that if this probability that I assign to this hypothesis is small, then that's going to make others agree that probably that hypothesis is false. Okay, so I don't think that you can directly do this. I think you have to go indirectly through some properties of that belief assignment, like how do I assign those kind of beliefs? And so these are necessarily some kind of statistical properties. So let's suppose that I'm able to establish this kind of claim that this event where I assign so it's an event in the Y space, this event where I assign some small probability to this hypothesis, that this one has a small p chance. Okay, so that if this happens to be a true hypothesis, then I would like for that to be a rare event with respect to this, the chance p. Okay, so then I think this gets us back into some of this classical statistics, and that's why I don't claim any real novelty here, but I've never seen Cournot kind of show up in this context, at least in the literature that I'm familiar with in statistics. So where you get back to Fisher is that, so his main thing was that, well, if you're able to assign this kind of establish some kind of claim like in the first line, then you'd be able to say that, well, if I'm, this implies one of two things happened. Either the hypothesis is false or some rare event has happened. And so then here's where I think the usual Cournot principle shows up, is that those p rare events, they rarely happen. So then what we've done is kind of roundabout through Cournot and related to some Fisher ideas that this, the thing that we wanted, we're able to get. So this is that small belief assigned to that hypothesis will suggest that others ought to agree that, well, probably that hypothesis is false. Okay, so that was the how I'm kind of seeing this Cournot related to these kind of things. Just a quick kind of segue. I know this is not really about the principle, but I thought that there seemed to be something related to this. So I had here a quick remark, but maybe I'm running out of some time. So I think what I want to do is skip over this, but I do think that somehow this kind of a next step beyond what Cournot is saying, what Cournot principle should suggest is related to this principle and how we ought to be maybe assigning these credences and chances, somehow linking them together, not just for the small probabilities and the rare events, but maybe for other kinds of things, non-small and non-rare events. But so about the best system, so I haven't talked about that yet. So this was something new to me. I hadn't encountered this, but I guess when I was thinking about what kind of interpretation I might assign to those subjective probabilities, I think it's natural to assign them a subjective one. But I think this is sort of artificial, and so I think that there's some reason to do that, but maybe somehow is a bit artificial. So what I was thinking about is, so maybe what does the best system interpretation have to say about this? So in Lewis's work, this is talking about like a kind of a balance of the simplicity, strength, and fit. I wasn't sure what exactly would be kind of the analogs of those things in this context. So I think it's a natural question. So what does it mean to be best if the system that we're trying to describe is one related to this sort of purely subjective thing on the inference side? So there's another notion to this kind of validity that I think seems relevant here is about efficiency. So this is kind of related to how there's in classical statistics, there's like a type 1 and type 2 errors, and you somehow are trying to balance between those two things. So roughly, efficiency is related to the magnitude of these probabilities. And so if I could somehow make those probabilities be small, I'm gaining some efficiency. But if I do that just naively, then I'm putting myself at some risk for violating this like validity property. So what I was thinking here was that maybe a way to think in terms of best would be trying to make these probabilities as small as possible, subject to this constraint that they need to maintain this kind of validity property. So then the idea is that, well, the interpretation I have for these beliefs is that they are what they are because the construction is both valid and efficient. And I thought I maybe I was thinking about that before, but I didn't realize maybe that might be related to this best systems business. But anyway, so just the last bit. So here is actually what the mathematical version of that kind of condition that I've been working with. And so anyways, my work has mostly been about how to construct some of these, call them your credence assignment rules. So how do you map the data into these subjective probabilities to satisfy this kind of condition? But I think that there's, I was mostly working on it from the statistical side, but I think there's definitely some interesting things here related to foundations and specifically Cournot and Lewis and maybe Deborah Mayo. So anyways, I think I'm out of time now, so I'll wrap up there.
Thank you very much, Ryan. This is really great. We already have some action on the comment side. It's a wealth of material there. I think we'll take our time to go and visit some of the discussions at the end. But for now, let's please welcome Professor Alan Hayek from Australian National University joining us here. Alan, do you have slides to share?
Just a very short handout, which I actually sent to Snow, and perhaps she will share it. And you can hear me okay? Everyone happy?
Yes,
Good.
that's right.
Thank
And
you.
we can see the Google Doc. Yes, okay.
Yep. All right.
Great.
And it's not essential, but it might help. Anyway, look, thanks so much. I'm delighted to be part of this panel. Now, in preparing for today, I found a paper of Glenn's very helpful. The one, that's what all the old guys said, the many faces of Cournot's principle, and it displays Glenn's encyclopedic knowledge of the history and development of Cournot's principle. Well, Cournot's principle does indeed have many faces, so much so that I would say that some of them are different principles. And my answers to the questions that Glenn sent to us depend on which face we consider. So just let's quickly go through some of them. They're on the handout. First, Cournot's principle, the principle that an event with small or zero probability will not occur, or as I would like to say that, all events of small probability will not occur. Now that's how I've understood Cournot's principle in the past. And it seems that the lottery paradox is fatal for this formulation on a suitable fine-grained carving up of events in a sufficiently rich probability space. All of them have small probability, yet one of them happens. So Cournot's principle, so stated, seems to have the absurd consequence that nothing will occur. We need some further qualification on the events, ones that are somehow special. They're the ones that will not occur. And the next formulation will do that. The next formulation, Cournot's principle says that an event of small or zero probability singled out in advance, underline that, will not happen. Okay, so note the added qualification, singled out in advance, and that helps make Cournot's empirical claim true. Most things that happen in the world are not singled out in advance by anyone. So the set of potential counterexamples of Cournot's principle is radically reduced. It's difficult to specify an event in all of its fine detail. Now, this formulation seems to solve the lottery paradox problem. One can't single out all events at the same time. Borel added that the singled out event should be remarkable in some respect. And that reminds me of Lewis's notion of a quasi-miracle. Now, remarkable is the opposite of typical, and that's what Isaac talked about. Okay, next formulation, Cournot's principle, probability acquires objective content only by its predictions. To predict using probability, you single out an event that has high probability and predict it will happen. Well, I think there are two different claims here, and neither implies the other. First, probability acquires objective content only by its predictions. Well, various Humean supervenient accounts of probability deny that. For example, frequentism and the best systems. Then the second claim, to predict using probability, you, and I assume there's a should in there, single out an event that has high probability and predict it will happen. And that's a norm on prediction. And then the last formulation I'll discuss, this is Glenn's summary for the seminar. Jacob Bernoulli equated high probability with practical certainty. Cournot suggested that this is the only way that mathematical probability can be connected with phenomena. Well, I would say that this does not connect probability with phenomena, rather it connects it with confidence. And it also sounds like a norm. If something has high probability, you should be practically certain of it. Well, provided you know that it has high probability. Anyway, as such, it sounds closer to the principle than the best systems analysis. And now moving to Glenn's questions for the panel, and especially the connection to the best systems analysis. First question, should Cournot's principle and Lewis's best system criterion be thought of as competing definitions of objective probability, you know, philosophers love to give conceptual analyses of things like objective probability. Now, like Isaac and like Ryan, I think that Cournot's principle is doing something else. I don't think that Cournot's principle is a definition of probability. I mean, and again, there are various formulations of the principle. High probability is practical certainty. Well, at best, that's a definition of high probability. It doesn't tell us, for example, what a probability of a half means. Practical certainty sounds like an epistemic notion. It sounds like a limiting case of subjective probability, not a matter of objective probability. By contrast, Lewis gave a definition of all probability, high, low, middling, and it's objective. Similarly, Cournot's principle, understood as a norm on prediction, not a definition. So what I thought was Cournot's principle until I read Glenn's terrific paper. Well, while that's objective, it's also not a definition. An event with small probability will not occur. Rather, it's a generalization about events of a particular kind, characterized in terms of a particular kind of probability, namely small. At best, it's a constraint on an adequate definition. Reject a definition that allows events with small probability to occur, though remember the lottery paradox. What are the advantages and disadvantages of Cournot's principle compared with Lewis's high probability as a measure of fit of a probabilistic theory to the world? Well, again, high probability is practical certainty. It doesn't sound like a measure of fit of theory to the world. It sounds like a norm on action and belief. If P has high probability, act as if you're certain that P. And I'd actually compare that formulation more to the principal than to the best systems analysis. It sounds like a special case of the principal, give or take. All events of small probability will not occur. Okay, well, that's about the world rather than belief. So that's closer to the best system analysis. I'd say that Lewis's measure of fit is more nuanced. It scores theories according to how probable they render what happens. But fit is just one dimension of what makes a theory best. Don't forget about simplicity and strength. What about probability acquires objective content only by its predictions? Okay, well, the best systems analysis denies that. According to that analysis, probability acquires objective content by what it says about the entire history of the world. Question 3, when, if ever, is Lewis's notion of perfectly natural properties and relations needed for Cournot's principle? Well, look, if we allow just any property, then there'll be counterexamples all over the place to Cournot's principle, understood as all events of small probability will not occur. You know, we can gerrymander high probability events that do not occur. Now, I said that we somehow need to restrict Cournot's principle to a special class of events. Well, maybe those that are somehow natural. That could be a natural narrowing down. But not that perfectly natural properties will save it from counterexamples. Again, I'm talking about the original formulation on my handout. I mean, think of a radium atom decaying exactly when it does, at least according to, the exponential decay law, has probability 0 before it happens. That's small by any standard, and yet I'm imagining it happens. And it's also the instantiation of a perfectly natural property. And that radioactive decay law, the exponential curve, could be part of the best system. It gains simplicity for being a continuous exponential distribution rather than some sort of discrete step function. Now, again, the version of Cournot's principle that says singled out in advance, that'll avoid counterexamples like this. I mean, presumably no one singled out in advance that exact decay time. So that would help. Natural properties. Now, they might be needed for Cournot's principle understood as a norm on prediction. One's predictions should be stated in terms of natural properties. But surely they don't have to be perfectly natural. You know, we should predict that future sapphires will be blue, but blue is not a perfectly natural property. It's somewhat disjunctive. It's shared by surface reflectances and phosphemes and the sky and so on. And then the last question from Glenn, Cournot's principle is vague. We must decide how high a probability is needed for practical certainty, which events with high probability are sufficiently simple or remarkable. Borel argued that this indeterminacy reflects the nature and diversity of probabilities applications. Well, I don't think that it's a case of indeterminacy. For me, indeterminacy means there's just no fact of the matter. Rather, I think the diversity of application is a matter of context dependence. The threshold for practical certainty, well, that depends on your interests. And that seems right. And that's a context dependent matter. Okay, I think my time's up. Thanks a lot.
Thank you so much, Alan, for the comments. Let's welcome our last panelist, our very own Snowjan, joining us from New York. Snow, do you have anything? Do you have slides you want to share?
Snow just messaged me to say that she's having some internet stability problems.
Oh, yeah.
So she said that if she can't get back on to ask the panel to move on, I mean, maybe we could make a few more moments to see if she manages to, but that's what she said over the phone.
So how about, well, there are already, interesting discussion happening on the chat panel. How about we perhaps start from and pick out some of those questions and have a discussion while we wait for Snow's return. I'm just going back into the chat's history. Barry, would you like to? So you asked a question about the bobcats. Would you like to elaborate on that one?
Well, this didn't really come up in the discussion so far so much, but I am curious about whether Cournot's principle and the principle are really in conflict or not. I'm not really sure what to say. I agree with everything Isaac said about typicality. And if he thinks Cournot's principle just applies to typicality, but not to probability, then I'm just not sure. But I'm wondering about, suppose that one thinks that it's 95% of the bobcats in some woods have short tails. That seems to be compatible with it being the case that the next bobcat, that the probability that the next bobcat comes out of the woods, me to see, is 0.95. It looks at first as though Cournot's principle is telling me to believe that the next bobcat, if applied to typicality, to believe that the next bobcat will have a short tail, whereas the probability prescription is, if let's say used as Cournot's principle, the principle is telling me to have a high degree of belief, or a belief that the bobcat will have a long tail. I want to know what to say. Is this a conflict or not a conflict?
Does any of our panelists want to take up on that question? I know that Snow has just joined us. Perhaps we could, put in our comments for Barry's question, and then we'll ask Snow to share her comments with us in just a few minutes.
Yeah, I can respond to Barry. I think that so two things. One is, and I typed this up in my comment in the chat if you want to see it. So one is, I think I agree that can happen, but given certain sort of pretty plausible, reasonable assumptions about the relationship between these two summaries, it won't. So So the chance fact is a certain type of summary. What I'm calling the typicality fact is another type of summary. And just far and away, it's almost always the case that the best sort of overall summary of the typicality facts and the chance facts are going to have probability measures and chance measures and typicality measures that agree, that are not diverging in the way that your example is saying. So that's like a first thing to say. It just won't happen, because if you think it's happening, it's a hint to you that either your probability measure is wrong, like your chance fact measure is wrong, or your typicality fact measure is wrong. Like,
so on Lewis's account of probability, it certainly can happen.
It can happen, but it's like
It typically will happen.
atypical.
No, it's typical.
I mean, it's like being in a deep. It's
It'll
like being in a
typically
deviant. Sorry.
It'll typically happen because Lewis's account applies to the whole distribution of fundamental events in the world. And it certainly could turn out to be the case. In fact, typically will be the case that in some circumstances, there will be a majority of certain events or a certain type. So that certain thing is typical, where the probability of that kind of event occurring will be very low.
No, I think it won't happen. The typicality measure you just used there is what I would say is the wrong typicality measure. There's a better typicality measure, or one that's more in alignment with the probability fact. The reason it's better is because it's producing a better summary, and part of how it produces
it's only the typicality of the whole universe that you want to apply Lewis wants to apply his best system account to.
What was the question?
Lewis's best system account applies to how fundamental perfectly natural properties are distributed throughout all of space-time.
Yeah.
Typicality, as people usually bring it up, applies to little local situations like the bobcats in the woods.
Yeah. So in my sense, it's just an example. The way you would use typicality is you generate all the kind of possible worlds, I mean, so if we're going to do it in the Lewis best system, which is not the best way to do it, you just look at all the possible distributions of perfectly natural properties across the mosaic. That just gives you a space of worlds, and you assume that the set of the power set of that set is the sort of thing that you can assign a mathematical measure to, and then you assign a measure to it that rules that worlds with where 70% of the bobcats have short tails are typical.
So Isaac, a lot depends where you get the measure from. If you're getting the measure from the actual world and the actual distribution of bobcats or fundamental properties, then yes, that'll be the case. But if you're just thinking about all possible worlds, then of course on typical measures that will come to one's mind, most of them might be ones in which the bobcats have long tails or short tails or no tails.
Yeah, I don't follow this thought. It's asking me that is like me asking you, where do you get the probability measure from? And the answer is very straightforward.
I know the Lewis's answer. It's the best part of the best systemization of the actual distribution of facts.
That's what I just said. That's where
I know that's so. I was saying yes, that's right. If you understand the typicality measure coming like that, but many people will understand the typicality measure coming a priori. I'm not saying you would. But this is the way many of the people who talk about typicality do. They think it comes a priori from just thinking about size.
The more charitable way I'd put it is I think other people think the typicality measure is a piece of a law, kind of like a type of chance, on a propensity view is a piece of a law. It's a priori in that sense. I don't know how a priori that is, but I think then they just say, yeah, it's just like, a kind of like primitive fact that this is the right typicality measure to use.
Isaac and Barry, I hate to interrupt this conversation. I think it's great. It's unfortunate. I think we might want to just, in the interest of time, let Snow present her views first, and then we come back to the discussion. Snow, do you want to share slides? Do you now still have the co-host designation, or you?
Let me see. No, I can't share slides now.
Wait, hold on a second.
I have to make me co-host.
Try again.
Okay, I think, yeah, it works. Thanks.
Great. Take it away.
And sorry, my computer crashed. Basically, that was what happened, and I have to change to another computer. So I feel like also, so I missed the latter half of Alan's talk, and also the very interesting exchange between Barry and Isaac. So I feel like many of the things I'm about to say probably has already been discussed. So bear with me. I'm also going to have a very short presentation. By the way, can you see the slides changing? Okay, great. So basically what I'm going to do is to share with you my confusion about this topic. I think all the questions that Glenn raised are very interesting. And as many people discussed, it seems that there are many phases to the principle, Chrono's principle, and there are many different ways in which it can be compatible, they may not be compatible, so on and so forth. So what I'm going to do now is just to introduce to you my taxonomy and the way I think about the issue. I should say that I'm not satisfied with this taxonomy or the diagram that I have here, but this is a starting point for me at least. So I was thinking, well, there are a bunch of questions. For example, you might ask about theta proposition P, you might ask about the physical probability of the proposition, you might ask about your subjective probability in that proposition, your subjective estimates in that proposition. You might ask the question, should you believe that proposition? You might ask whether or not the proposition is true. And like as I pointed out, you could also ask a different question, whether or not the proposition is typically true and how these different questions relate to each other. So something that we have already discussed in this panel series, for example, according to Lewis, physical probability is connected to subjective probability via the principle. Exactly the nature of the principle is up for debate. You might also think that the subjective probability is connected to belief via something like a threshold principle, the Lockean principle, again, very controversial. And lastly, as Isaac pointed out, there's also you might also think that typicality facts have a connection to belief via the typicality principle, which you might think is itself connected to the principle. One might entail the other or whatever. The relationships are controversial. But anyway, so I was thinking this is a diagram that we can use to picture the kinds of things that we might be asking and how they might be related to each other. So that's a rough starting point. But as I said, I'm not happy with the diagram. In particular, the arrows in the diagram, they're not supposed to suggest anything very substantial. But before sort of scrutinizing the diagram, let me just mention another kind of probability, which I think might be, so I was convinced until last Monday that when Glenn talked about Cournot's principle, I was thinking that is sort of similar, if not just a version of the typicality principle that Isaac was talking about. But then when I hear the discussion between Glenn and Barry and Phil, then I realized probably Cournot's principle could also mean something different, and here's how. So you might think there's a different, well, not necessarily a different kind of probability, but there's a kind of probability, which for the time being, I'll just call it a probability in a model or a theory. So the kind of things that I had in mind is there's the following probabilities. By the way, this is just an example I extracted from Sinner's textbook, An Introduction to Stochastic Processes. And here he was like, well, suppose at a certain fork on the road, about 62% of the vehicles turn left, then let's build a stochastic model, take xn, the random variables, to represent whether or not the vehicle turns left or right, and then make a bunch of independence assumptions. Then the xn is a Bernoulli process with probability 0.62 for success. So that's a standard example you might encounter in a probability textbook. And I think the interesting question, for me at least, is it's not obvious, at least not immediately obvious to me, that the value 0.62 fits any of the things that we have on the diagram before. It's not entirely clear that it is a probability ascribed to some physical event, for example, you pick a driver and ask whether or not they will turn at the particular fork, or your say a type of events, whether drivers will turn at this particular fork, or someone's like the modeler's subjective estimate of that event. Instead, you might think, well, this of quantity in the model, and it's another question how that quantity is related to the reality. And I'm not saying that they are not related. So just as an example, you might say, well, the Russia as the picture represented on the map that is larger than China as represented on the map. And in fact, Russia is larger in China. What happens in the representation could be very intimately connected to the reality facts, but it's just saying that we should make the distinction while not denying that they're not connected to each other. So bear that distinction in mind. Now we can complicate the diagram by adding a third component. As I said, it's not the third component, it's I guess the sixth component, model theory probability. And as I said, it's not like the model theory probability has to be a different kind of probability than anything that we have on the diagram. For example, some people might think subjective probabilities, they're just mathematical constructs that we use to represent someone's static state. So ultimately there are model probabilities, or you might think physical probabilities, there are ultimately model probabilities. I'm open to all these possibilities. It's just that there's a conceptual distinction we can keep in place and ask the question, how does a model probability or a theory probability relate to all the other things that we have on the diagram? And in particular, I think this is where we can reinforce the distinction that all the panelists have already alerted to us. So it's the question that we're asking when we consider, for example, Lewis' best system account of lawhood is we're asking about the truth condition. What makes the theory true? And in particular, in this case, what makes a probability theorem or probability statement of a theory true? And that's at least conceptually speaking, different from the question of rational acceptance. What makes it rational to believe or have high confidence in a theory being true? The fact that you should believe a theory that it is true on the basis of some things doesn't mean that those things are grounds or truth conditions for the theory. So those are two different things. And then now let's move on to Lewis' best system account of lawhood. Actually, for this audience, I will just stream the condition because I think all the everyone here in the audience are already familiar with Lewis' best system account of lawhood. But basically, I think if I have to put Lewis somewhere on the diagram, I would probably put it here. I have a question mark here because first, Lewis thinks that the best system account applies to true regularities, and secondly, it doesn't apply to models. So there are a bunch of qualifications we have to make, but if I have to put it somewhere, it's probably here. On the other hand, Cournot's principle, as Alan points out, it has many faces. And here I'm just using one statement of Cournot's principle that I learned from Glenn's presentation once. So this is the principle that says a physically impossible event is one whose probability is infinitely small. And this remark alone gives substance and objective and phenomenological value to the mathematical theory of probability. And I think, as Alan points out, there are multiple interpretations of that statement alone. And also we should bear in mind that Chrono had different statement formulations of the principle, it seems like. So at least there are three different things we might mean by that statement. First, you might think, well, that means if the physical probability of P is infinitely small, then P is physically impossible. That's a bridge principle between physical probability and physical possibility. Or you might think, well, it's a bridge principle between model or theory probability on the one hand and physical probability on the other. Lastly, you might think it's a bridge principle between model and theory statement and rational belief. So I think all three versions have already been discussed in this panel, which means that we can at least put Cournot's principle at three different places in this diagram. Okay, so that's my taxonomy. As I said, I'm not entirely satisfied with that, but hopefully that is helpful in a way for you to sort of put everything together in a picture. Okay, so let's go back to Glenn's question. Well, actually, I'm only going to address the first and fourth question. The first question is whether or not Cournot's principle and Lewis' best system criterion be thought of competing definitions of objective probability. And the answer is no, I don't think so, though I agree with the previous panelists. I'm not entirely sure how to read Cournot's principle as a definition of objective probability, partly because we can parse out the principle in so many different ways. And now moving on to the fourth question, I'm going to skip the second and third, moving on to the fourth question. Do you think that the vagueness of Cournot's principle reflects the diversity of the nature and the nature and diversity of probabilities obligations. And I think, yes, though presumably that depends on the kinds of diversity at issue. In particular, I think there are, again, a bunch of distinctions that we can draw. We can distinguish between different kinds of probabilities, the same probability, but different kinds of beliefs, whether or not, so going back to the login question, whether or not you have the same probability, should you believe something or not, that might depend on the context. And lastly, you might think same probability, same belief may nevertheless lead to different decisions depending on the state at the issue. So basically, I'm just echoing back all the points that the previous panelists have made, that the questions are interesting and hard to solve, and maybe we can start by sort of disentangling different questions in the vicinity. And that ends my presentation.
Thank you, Snow. All right. And thank you to all the panelists for your wonderful comments. As you have seen, we have already started a great discussion. Let's come back to some of the questions that we've been talking about in the chat. I think Glenn and Alan and Barry, you have been discussing this contrast between whether Lewis' best system interpretation is Bayesian or not. Does any of you would like to elaborate on that? Or maybe Glenn, you can frame your question for the audience.
Sure. The way Lewis stated the best system idea, and the way I've seen Barry repeat it, says that fit is defined by, there's this strength, fit, and simplicity. So focusing on fit, Lewis said, well, fit would be defined by giving the biggest probability you could to the actual human mosaic. So Cournot has a different way of measuring fit. He looks at simple predictions of the system as a whole. And it seems to me both of these are talking about evaluating the system as a whole. Neither of them is focusing on an individual probability. It's all justifying individual probabilities as part of a system. They both seem to have that in common. That's an aside, and I don't understand people telling me that best system is justifying individual probabilities that Cournot is not. But just focusing on the question of fit, my question, and it's really a question, is whether people who are talking about best system are all insisting on this Lewis's deal about making it maximizing the probability of the human mosaic, or whether that they would consider Cournot kind of statistical tests as another way of measuring the fit. That's an honest question. I've heard Barry's view, but I haven't. There's a lot of people here that are talking best system.
What is my view?
Pardon?
Oh, you said you heard my view, but
I don't
what is
misrepresent anyone.
view?
Okay, I think I've asked my question.
Can I ask Glenn to tell me what my view is? Because I don't know what to say.
No, I forget about my. I said what I thought you had said, but it doesn't matter. I have a question here on the table. That's all. Tell me
that's
what.
a really good question that you asked.
Yeah.
Actually.
Nobody has a response.
I could say one thing. So Lewis was very quick and somewhat sloppy in his criteria for what counts as a best system. He was quite aware of this, and he knew that much more had to be said about it. His account of fit just doesn't work right, as was pointed out by Adam Elga in a paper a long time ago, because it ends up assigning too small a probability. So it needs to be made fancier in some way. Now, whether it should be made fancier in a way by using some different way of measuring how good a probability theory fits the world or not, that's an interesting question. I don't see his account does make use of likelihood, and that's part of the Bayesian idea, but there are people who are likelihood theorists who don't consider themselves Bayesian, but this may be just terminological. I don't know.
I did also raise that question, and Alan said, oh, where's Bayes? But I didn't mean I was referring to a feature that likelihood and Bayes have in common, which is that in a non-parametric situation, it's practically impossible to implement. And I don't think we have a parametric model for the entire Humean mosaic. So what it really means is very hard to get a handle on. You know, if you look at the literature in stat, where people have tried to do non-parametric Bayes, it involves all kinds of arbitrary modeling and sequential kind of digging deeper. You can't just take the whole thing and say, oh, let's look at the best probability fit. Doesn't make, well, I don't want to be dogmatic, but it doesn't seem to make very much sense. Doesn't seem to work.
Right.
Whereas, yeah. And so it seems to be a contrast there between, you know, you can implement the Cournot idea in a non-parametric context. You know, that's in my book with Wolf, in a way that's not so clear. I don't say for the whole world at once, but still, you can get farther than with the sort of likelihood idea. That's, I think, and it's two contrasting ways of talking about fit. It's the two contrasting ways that are familiar in the history of probability and in math stat. So that was my question. Are people who are talking best system wedded to the one or the other? Likelihood versus statistical testing.
Can I jump in? Maybe this is just a terminological matter, just to get clear on what we mean by Bayesian. We could mean a couple of things. We could mean somehow we essentially appeal to Bayes' theorem, but it could also mean subjective probabilities play an essential role. And now, of course, there's a distinction between subjective and objective Bayesianism. Anyway, I just wanted to make clear that there's nothing subjective about the best systems approach. And maybe Glenn wasn't saying there was, but that when I saw his comment about Bayesianism, what triggered in my mind was something about the important role of credences, subjective probabilities. And there's nothing of that in the best systems analysis.
Well, I was substitute likelihood then, if that.
I say
I don't think likelihood has its own problems, and you almost have to regularize it with something that looks like Bayes. But just say likelihood to avoid the subjective.
Certainly, there's a likelihood. That's one of the components in the best systems analysis. Yeah.
But still, I don't hear anybody giving an answer to my question, which.
I don't know though.
Go ahead, Alex.
Oh no, I was just gonna say that I don't know the literature on this or what Elga's proposed fix was. I mean, I was thinking one naive idea would be there are notions of sort of the accuracy of a credence function relative to a world. Maybe that could be adapted to the context of fit, the accuracy of a chance function at a world. But I don't know if that would I don't know if that would face the same technical difficulties involving infinite, infinitary cases as the more naive suggestion. And I don't have a sense of how that contrasts or doesn't contrast with like the Elga proposal, for example.
And Ben Levenstein, a good Rutgers product, has that kind of view for understanding fit.
Okay. And that would be like the Breyer score or something. I'm sorry, Isaac.
The way is to just think of things the way I think that Isaac was thinking about things. Is think of Lewis's probability as really being typicality, and then measure whether or not a theory fits the world by whether or not what it says is typical is what happens, and whether it says is atypical doesn't happen. Then you'd be using something like standard statistical testing. So I can imagine somebody developing that idea.
Yeah, and I was going to say, I think that's kind of in Elga's paper, so I can't really remember, and I was trying to scramble to find it. But
Elga does it with taking special propositions that are the ones
right.
with. So
right. But
I have a version that's something similar to to Elga, but it has to do with macroscopic propositions.
But my memory, was this right, Barry? My memory was he was doing that like the reason he's focused on test propositions is basically because of a kind of reference class problem in the background that he's worried about. Like if we focus on all of them, then we can jerry rig any world, like we could give a justification for any what I'm calling typicality measure to be the correct one by which to adjudicate fit. So we need to focus on only these select few test propositions when determining fit. In other words, it's kind of like like the naturalness issue.
Yes, that's right.
Yeah, that's so for that reason,
my macroscopic thermodynamic propositions. So naturalness is not Lewis's notion of naturalness, but it's in the neighborhood.
Yeah. I was just going to ask for Glenn to say a bit more about the proposal, because I think I didn't really follow how it works.
Well, this whole best system thing is difficult for me to follow how it works. It's, it's just so asymptotic. But if you somehow are looking at a probability distribution and then you're looking at or a probability measure and you're comparing it to what you see, one way of doing that is by statistical testing, and that's Cournot's principle. And so I was just asking, is that a version of best system that's acceptable to our philosophers? Or is, but I think you answered to me. I think you said yes. I think I've heard that. So in that case, Cournot's principle and best, and since Cournot's principle also has the business of simplicity involved, and since how far you can go in depth, you can't, well, I'm saying Cournot had this idea that there were humans who had their go at objective probabilities, but there would be some kind of demigod who wasn't God, but who had a better view of everything that was going on, who could have their objective probabilities. So, next time we talk, we'll have this sort of thing about levels of objective probability, and and I think we'll learn something there. In my opinion, we'll learn that Cournot's principle is the only thing that'll work if we want to look at different levels. But aside from that opinion, I can see how that goes with Cournot's principle, how you can go deeper. Step by step by step. What sense there is to sort of getting to the ultimate, I have a hard time seeing what's being talked about there.
Glenn, when you say work, that's really a question, because I think the work that you think you want to do is really different from what Lewis thought the work that his account was supposed to do. Not a conflict, but just different work.
Well, I don't quite see that, Barry.
Lewis wanted to know the truth conditions of probability statements. What is it about the fundamental world?
Why can't it be the truth condition for an entire probability system?
It's for all probability statements.
Yeah,
Lewis
but he has given
that's
them.
not Lewis's view. Lewis is saying them, he's going to give an account of what makes probability statements about our world true or false. You might not like this. You might think it has.
But isn't it ultimately is it ultimately not a statement about individual probabilities being true or false, but a statement about the whole system being correct or not? Isn't that right?
Yes, that's right.
Well, that's what Cournot's principle was doing too. The statement about whether the whole system is.
The difference is this: the systems you're imagining applying it to, for example, might be a particular theory in biology to see whether or not you ought to accept whether a certain drug is effective or not. You might apply Cournot's principle, and that you might have a probabilistic model of that theory, and Cournot's principle might tell you to reject that particular probabilistic model. That might well be, and it might even be right, but that's doing something different. Lewis wants to know what makes the probability claims in that theory right or wrong.
Well, what makes
what
he's not
makes
saying whether the whole
them.
model is right or wrong. Doesn't it fall
What?
or does it fall by its as a doesn't it stand or fall as a whole?
Not with physics. The thing in, I mean, I think they'll be connected, but the particular probability model that you're testing, somebody might want to apply Lewis's idea, not Lewis, but somebody might want to apply it to a particular theory in medicine, let's say, and say the probabilities there are given by best systematization of various kinds of claims about the efficacy of various kinds of drugs. This isn't Lewis's view, but it could be somebody's view. Then those are, it is a
And they would not be,
system.
and they would not be claim. And okay, so that's a best system locally, and it might be completely different than Lewis's ultimate best system. Is that what you're suggesting?
That's right. So like you said, this will come up next week for sure.
Yeah. Well, I mean, it's true, I would say that this idea of having a probability model for everything, well, Cournot basically had the idea already. And, he used Cournot's principle to interpret it. But what Cournot and Lewis are trying to do in terms of this sort of idea of a best system for everything is something, pretty hard to get your hands on. And it's true that statisticians use more local models. That's all we can really, that's what we can really work with. It's not going to change. Mm-hmm. That's right. We're agreed there that Lewis and Cournot had something more ultimate in mind than than the statisticians are doing. Yeah.
Completely. From the bit of Chrono I read, which is via you, I would like to get a hold of the whole book in English. But when I read you, what occurred to me is, well, Cournot basically anticipated Lewis. He just didn't have some of the fine-grained, he didn't have, nobody had developed Bayesian inference prior to him in the way it did. But if Cournot were to come back today, he would say, boy, Lewis was what I was thinking of.
Okay. I don't know what you meant by develop Bayesian inference. Cournot had seen Bayesian inference and he had a very low opinion. Mm-hmm. Sorry, someone was knocking on the door. I apologize. Please carry on.
I am looking at the chat. So there are a few more questions that were posed. Glenn, you have several. Maybe this is jumping a little bit, kind of mixing the order, because you had one post that was asking about, I believe it was a comment that you posed in response to Alan's comments, and you asked, it's probably one thing if there are a lot of uses, we may need different interpretations of probability as well as different interpretations of Cournot's principle. And I want to see if we want to perhaps discuss this, because Kamal Gersoy also posted a question that was asking about the categories of probability. So perhaps that we could discuss next.
I had a question related to this, but I don't want to jump ahead if Glenn, you wanted to clarify what you had in mind.
Well, I think Alan sort of responded to it already, or maybe I'm confused, but I don't have that's. Alan was saying there's lots of different, was pointing out that all these different versions of Cournot, and I think he agreed they might apply to different situations.
Yeah,
Alex,
I was going to ask.
Do you want to add something?
Yeah, I was actually going to ask, related to Snow, one of the things that you brought up was like the theory/model probabilities, and I was just curious if were you understanding those as kind of like uninterpreted probabilities that are sort of like there in our representations, what seem like candidates for probabilistic representations, but haven't yet been interpreted? Or perhaps were you thinking like, no, this could actually be another type of probability in like a stronger sense, that then if we were to focus on like Cournot's principle framed with respect to that type of probability would have would make a difference to what we thought of Cournot's principle. I was just curious to hear more about what that idea of a theory / model probability was.
Okay, I'll just quickly answer. I hope this is also related to the previous question. So I basically didn't have anything sophisticated in mind. In particular, I don't want to say there's another kind of probability. Woohoo, there's a new kind of probability called theory / model probability. I think it's I mainly brought it up to try to clarify the question, because I feel when we want to understand, for example, like in the Bernoulli process, you face this question in the problem set, and when you are doing application, you might construct a simulation model and then say, okay, here's the probability that the driver is going to turn left or right. So what is that statement meaning? It may not mean probability in the more substantive sense. In particular, you might think, actually, I think the most amount of the work would have to do with interpretation of what the random variable represents. What each random variable at n, they say, well, that is the at n equals 1, just in case the driver turns right or wrong, turns right or left. But obviously, it doesn't necessarily represent any physical event or even type of physical events that we might have in mind. And also, the independence assumption may not hold. So it seems that it's more like a hypothetical model, idealized in all sorts of respects, and then it gives us a value or quantity in the model. Question is, what is the practical significance? Practical in terms of both physical representation and practical decision-making, practical significance of this model. So I was thinking that when I was reading some of the quotes that Glenn brought up with respect to Cournot's principle, I felt some of the principles might actually have to do with interpretations of this kind of statements, probability statements within the model and what is practical upshot. And that seems to be a different question than how physical probability relate to belief, how physical probability relate to reality. So that's the reason. Yeah. Sorry, that was longer than I thought, but yeah.
Are you thinking that it could be analogous to like framed this way, that Cournot's principle could be somewhat analogous to a principle about like when we have a formalism, say, of a physical theory, how if at all we should read off what that physical theory says about, I don't know, the ontology of physical world or something like that? It's sort of, are you thinking maybe it could be doing a sort of parallel role to those kinds of principles, that it's telling us, given a probability theoretic model, when we're licensed to think of its representations as actually representing probability, I guess, I don't know, as opposed to what, and this gets into what Isaac was saying also about distinctions between probability and size. Yeah, so that's a complication. But anyway, yeah, is that sort of what you're thinking?
So I definitely think it has to do with our theory of representation and in general, how the representation or model connects to reality. You might think that all models are false, but yet some are closer to reality than some others are. And Cournot's principle comes into place, not telling you, extracting the true content from the theory, but rather giving you some kind of approximate isomorphism that would be helpful, something like that. So I think I'm open to these possibilities, but I thought it might be interesting just to tease apart this aspect of the question. But totally, I think the more we dive into it, the more complicated it seems. So yeah.
Well, this is a little off topic, but it's something that came to mind as Snow was talking about physical. I think, and I may be wrong, but I think that when Cournot was using the term physical impossibility, the contrast was with metaphysical impossibility. He was saying that so physical impossibility meant that in the real world it's not going to happen, as opposed to it being theoretically impossible. Maybe that was clear already, but in the past it has confused me. I had another question. Everyone has fallen silent, and well, we don't only have 10 minutes. But I posted another question in the chat was, when people talk, those who talk about best system, are they thinking that the best system is a stochastic process where probabilities are dependent on time and space?
Yeah, I think so. On one way of thinking about it, you have a bunch of, you can think of it as like a bunch of conditional probabilities where you're conditionalizing on different segments of the initial history of the world. So the picture is something like this. For every initial segment, there exists a chance, function that describes all the chances of all propositions, sort of conditional on that segment being the initial segment. So there's actually a bunch of different chances.
Well, this came to my mind when Barry was talking about, well, things might be different locally. Surely to some extent, your best system would take that into account, the locality into account.
Yeah, what did you have in mind by that, Barry?
Yeah, I mean, as I think you've heard before, and you'll hear about, I guess, next week, I think that the probability distribution provided by statistical mechanics ends up assigning a probability to all possible histories of the universe. That ends up assigning probabilities to all physically specifiable propositions, so to all conditional probabilities. And so statements in higher level languages either are going to agree with those once they get translated into the lower level language, or they're going to disagree. If they disagree, there's a problem, because who should you pay attention to?
I didn't follow that. Maybe others did.
So you were wondering, gee, how can anybody in their right mind? I'm sure you didn't have me in mind when you thinking that. Could think that all of these propositions have probabilities, including propositions like there's a certain probability that Trump will run for election given the macroscopic state of the United States now, or something like that. So in my view, statistical mechanics assigns that a probability. I'm not saying we know it or we have access to it, but that there is such a probability. Now, not everybody who understands statistical mechanics understands it the same way I do. So there's arguments about that. But if you understand it that way, which is not an unusual way, then since Trump's running for re-election is some sort of situation in which there are various, whatever, quantum mechanical states or particles moving around in various ways, and so on. There's some giant set of those, and this macroscopic state of the world right now, there's some giant set which corresponds to that. There'll be some conditional probability of how likely it is that Trump will run for re-election given the macroscopic state of the United States now. And I see Harry giving the look is, who cares about that? And I agree that no statistician should care about that. But I think philosophers should care about it. Okay, but I won't go into a side story about why. But my claim is that there is such a probability on this view. And if there is, then you got to wonder, how is that going to be related to applying probabilities at higher levels? Are they going to fit together or not fit together? And if they don't fit together, they're going to be telling you, or could be telling you, different things about what to believe or how to act. Does that make sense, Glenn?
Well, fitting together is not very specific. I mean, certainly the probabilities with different levels of knowledge will not be the same.
If they're not, then you've got a problem. It's as if you had
no, you agree that they're not. What your probability is depends on what you know. Right? Do you agree with that?
No. the probabilities that there ought to be the same. So think of probability, and this is what I think Lewis was thinking about it. Probability is kind of the world's advisor for creatures like us who can't be Laplace's demons. Probability will tell us as much as somebody could possibly get if they're in our shoes, way beyond what we actually can get, but our shoes. We can't know the precise momentum positions of all the particles, of course. But probability is giving us a probability distribution over the macroscopic propositions, over the microscopic propositions, which will determine probabilities over the microscopic propositions from that. Since statements in biology or history or economics ultimately are true in virtue, I think, this is what a physicalist thinks at any rate, in virtue of what's going on at the microphysical level, there'll be probabilities that they will inherit from the microphysical level. There are issues that complicate this, like vagueness, but that's basically the picture. And so if you think of probability as this ideal advisor, it'd be like having two advisors, the ideal advice from biology and the ideal advice from physics. If the ideal advice from physics is really the ideal advice, and also you have this perfect translation from physics to biology, it better be that the ideal advice from biology is completely compatible with the ideal advice from physics.
Another way to put it is in terms of differences of description. So the same event can be described macroscopically and microscopically. And understood that way, what Barry is saying is the probability assigned to a macroscopic description has to equal the probability assigned to the equivalent microscopic description. Because if they don't, then you're getting two different recommendations about one and the same thing. So
so if a conditional probability has two parts, the condition and the event, you're just talking about the one side.
No, I'm talking about both sides.
Yeah.
I mean, Isaac is talking about. Are you going to describe the condition at different levels as well?
Yeah. So if you're looking at a conditional probability statement, it takes two propositions and outputs a chance or outputs a probability. Those two different propositions could admit of two different descriptions. You could describe each one using macroscopic vocabulary about, using names like Trump and using predicates like is an election. There's a second way Barry's whole concern is predicated on the assumption that there's a second way you could describe the exact same sort of thing. You could drop names like Trump and instead use long descriptions like this particle is here and this particle is here, and together they compose like golden hair.
I'm way out of my depth, and we should let other people talk in a few minutes remaining. But if on the condition side, if you have a more detailed description, you have more knowledge, and that's going to give it a probability. That's all I was thinking. But let it go. Because we do have other people wanting to talk.
Just to let me finish, the main thing is that your knowledge can also be described in two different ways. It can be described in this macroscopic way and in this microscopic way. And then that's going to generate the same problem that Barry keeps describing if the two descriptions correspond to two different types of probability.
All right, thanks, Isaac. You often know what I'm thinking better than I do.
So we got maybe 1 minute left, and Marshall, I do want to invite you to perhaps say something about, because you have put in several comments about different things, but for the a minute that we have left, would you like to maybe highlight some of the things you were saying in the chat?
Yeah. Okay. Well, they're actually so. I'll go to the first point, which is, and this is really, I think I'm just saying the same thing as Snow, maybe in a different way, or putting a different, adding to it. So you could use a model. It seems that you can use a model, say, to predict the frequencies in a system, and predict the number of left turns. I forget if it was left turns or right turns. And you might do that by assuming, like by pretending that for each turn, there's a probability of 0.62. And then you use, do some quick calculations and you say, oh, there's a high probability that the relative frequency of left turns will be 0.62. But just because you do that calculation doesn't necessarily mean that there's actually a probability, a single case probability for each turn in the world. It could be that this is just a useful way to do the calculations, a useful way to model it. It could be that there really is true that in some sense there's a high probability that the relative frequency will be 0.62, but the attribution of probabilities to individual turns is just an artifact of the way you proceeded. So the probabilities that are formally attributed to each turn don't actually refer to anything. That's a possible view. That's all. And here, let me just say, when I say refer to, I'm speaking as a philosopher with this idea that one question you can ask about a model, whether it's a model, a statistical model, or any other kind of scientific model, is in what sense do the terms in the model refer to things in the world? And maybe they don't in some cases, or maybe it's only approximate.
Great, thank you, Marshall. Well, we are officially out of time. I know this conversation is not quite over, but fortunately we do have 2 more panel meetings to come, not the next week, in fact. Snow, you will remind us, I think in 2 weeks, we're gonna reconvene for the 5th panel of the session, and everybody, of course, is welcome to join. Just full disclosure, we will be saving the chat from today, and these are all recorded sessions, and you can find it on YouTube. If you want to point to your colleagues and students about today's meeting, you're more than welcome to do. And well, thank you again for all of you for joining us, and we hope to see you again in 2 weeks.
Thank you, and thanks so much, Robin, for moderating.
Yeah,
Oh, thanks to you for
Robin.
doing
Thanks,
all the
everyone.
heavy lifting. Snow is the one who should be thanked for that. See you all.